This video provides with information for the startup of RTD temperature probes. Beside the general information, the video shows the connection types for RTD temperature probes and the setting for the evaluation unit. RTD temperature probes change their resistance in the case of temperature fluctuation. Platinum has established itself as resistance material in industrial measurement. The properties of the so-called PD100 and PD1000 sensors are defined in the standard DIN EN 6751. Among others, there is defined the characteristics and the tolerance classes of the sensors. A PD100 has a basic resistance of 100 ohm at 0 centigrades. At 0 centigrades, the resistance changed by 0.391 ohm per Kelvin. The resistance change isn't linear over the measurement range. In the easiest case, the RTD temperature probes can be connected via two wires. Normally, JUMO field devices offer universal inputs. The inputs can be used for 4 to 20 mA or 0 to 10 volt signals. Furthermore, thermocouples and RTD temperature probes can be connected. For setup of the components, configuration programs can be used. In this program, it must be done the setting RTD temperature probe for the corresponding input. The field device then gives a direct current into the measuring circuit and measures the voltage drop. When linearization linear is selected, the field device displays the measured resistance. When linearization PD100 is specified, the field device forms the corresponding temperature directly from the measured resistance. The measured resistance corresponds to the sum of sensor and wire resistances. There is a systematical higher resistance and thus a higher displayed temperature. The 0-point adjustment is carried out with most JUMO field devices by entering the line resistance. An example: if the resistance of the lead of a PD100 is 2 ohms, the temperature display is about 5 Kelvin too high. The 0-point is adjusted after input of the line resistance. With a 3-wire connection, the voltage which is dropped down on the sensor and the conductors is measured as well. Beside this total voltage, the drop down at one conductor is measured. The double of this voltage is deducted from the total voltage. By this, the voltage drop down at the RTD is determined. Precondition for an exact result is the same resistance value for the two conductors through which the current flows. 3-wire connection is most often used in industrial measurement. With respect to the wiring, the 4-wire connection offers the highest accuracy. The voltage drop at the RTD is directly measured. In the case of a 4-wire connection, conductor and terminal resistances can be different without this affecting the measuring result. RTD temperature probes can be equipped in 2, 3 or 4-wire technology. But the characteristics of the PD100 applies only to the sensor, including 10 up to 30 mm connection wires. When using 2-wire technology, the probe connection cable leads to a higher resistance value, and thus a higher temperature will be displayed. The shown classes are defined for RTD temperature probes according to DIN EN 6751. The Class AA thermometers allow the most accurate measurement, while Class C thermometers have the biggest tolerance. In practice, Class B elements are often used. For a measurement at 300 centigrades, the tolerance is plus minus 1.8 Kelvin for a Class B thermometer. For the design of thermometers, DIN EN 6751 states: Thermometers with accuracy class better than class B are to be designed in 3 or 4 wire circuit. RTD temperature probes in 2-wire technology can be connected to a field device starting from a connection point in 3 or 4-wire technology. From the direction of the field device, the lead resistances are compensated up to the connection point. Only the probe connection cable leads to an offset in the temperature signal. As described before, a systematic higher temperature display results in 2-wire circuit, but this can be eliminated by a 0-point adjustment. The table shows the offset for a PD100 per 1 meter connection cable. If, for example, a cable with a cross-section of 0.34 square millimeter is used, the offset will be plus 0.27 Kelvin per 1 meter cable length. In case of a PD100, a line resistance of 1 ohm corresponds to a display which is approximately 2.5 Kelvin higher. In the case of a PD1000, 1 ohm line resistance is only reflected in an approximately 0.25 Kelvin higher display. If the accuracy requirements are not particularly high, the use of a PD1000 in 2-wire circuit can be sufficient. For 2-wire circuit and the use of a connection cable with a cross-section of 0.34 square millimeters, the offset will be only 0.027 Kelvin per 1 meter connection cable. Thank you for your attention.